Let's wait for few more minutes. um, let few people join, and after that we'll continue our session. We have already discussed earlier about the wavelength modulated sensors. Today we are going to discuss about the continuation of the discussion which we are carrying out throughout the last 2 weeks or two sessions. Today we are going to discuss about the wavelength modulated sensors for various applications. One of that is structural health monitoring, which has been shown in this first slide. And structural health monitoring using the wavelength modulated sensor contains an architectural synthesis of FBG interrogation and stimulated Brillouin scattering. You can see here there are so many things are mentioned in the graphical representation. X-axis is a wavelength, and y-axis is the power. Then you can see here that FPG peaks are mentioned over here. Then the shift in the wavelength. This is the input side. This is the input and feedback one. Scattering, reflected beam. Then has the Brillouin gain spectrum also, and pump probe signal as well. So what is the target specification here for the structural health monitoring or health structure infrastructure, health structure monitoring sensor? So in that, acoustic emission should be in few kilohertz, 10 kilohertz to 1 megahertz, nanostrain resolution, and true distributed sensing, which is a very challenging part. How we can overcome these things? The economic imperative for condition monitoring. The optimal structure health monitoring exists at the interaction where the cost of continuous optical interrogation is less than the cost of catastrophic structural failure. You can see here total cost, corrective maintenance, preventive maintenance, and in a x-axis it is a test frequency low to high, and operational repair cost. You can see here that if you are going from low to high, the repair cost obviously operational and repair cost decreases, measurement cost increases towards the high, and total combined cost will be in the middle of somewhere to the low to high. Yeah, so instrument also, the measurement cost majorly depends on the instrument cost. So it can be balanced between both low and high. So the cost of operation and the measurement can be combinedly um, balanced to have a better healthcare monitoring system, healthcare um, uh, cost effective health um, treatment or something which is combining this. So the thing is, ultrasonic detection is the earliest precursor to structural failure. You can see here that the standard interrogators operates at kilohertz speed. To capture 1 megahertz ultrasonic precursors, interrogation must shift from slow spectral scanning to high speed optical filtering, and for that you can see here the system failure terminal point. Then it moves to the first thing is here, acoustic emission ultrasonic wave 10 kilohertz to 1 megahertz, and which has the time to failure discovery. Why? Because the system failure, then thermal signature, low frequency static, vibration changes, low frequency causes statics, and the mechanism is micro cracking generates pressure wave that stretch and compress local fiber Bragg gratings, and that's how the micro, because of the micro wave cracks, pressure waves generates. Let somebody join. Yeah, so we are in the second slide and discussing about the health structure monitoring system. Yeah, Janani, can you see my slide? Is it visible? Okay. So we in this week we are going to discuss about the wavelength modulated sensors, the extended part. I'll just briefly introduce you what I have discussed till now. So wavelength modulated sensor for various applications we are going to discuss. One of them is the structural health monitoring, and for structural health monitoring, you can see here that one plot is mentioned where there are so many kind of signals are there. The FBG peak is there, blue and green spectrum, pump probe signals, and can you mute yourself? Yeah. So the target specs are acoustic emission, which is 10 kilohertz to 1 megahertz. It should have nano strain resolution, and it should also have two distributed sensing for health structure monitoring. Okay, this one. To what is the um, problem here? The problem is economically it's very cost is the problem for that. So economic imperative for the condition monitoring. So if you go from the low frequency to high frequency, the operational or repair costs will drastically decrease. You can see here that repair cost drastically decreases. Why? Because we will get the proper um, analysis or proper diagnosis to for what we need to treat it. But what about the measurement cost? Once we are going towards the high frequency test, um, so what is happening is the measurement cost, the instrument which is giving the diagnosis um, data, the cost will increase for that, and they will charge more. So using these two things we can combine, and we can say that the total combined cost can lie minimum at somewhere here, neither at low nor at high. So we need to have the corrective maintenance and the preventive maintenance, middle of that somewhere we can get this cost effective treatment. For that, first thing is that ultrasonic detection is the earliest precursor to structural failure. So what is happening here that can be possible that structural failure, thermal signature, low frequency static thing, and then vibration changes, low frequency quasi-static. Also the acoustic emissions, ultrasonic waves, 10 kHz to 1 MHz. What is the mechanism behind this failure? The micro cracking generates pressure waves that stretch and compress local fiber back gratings. You can see here micro cracks generates the pressure wave, and because of the stretching and compressing localization strain, this grating also affects so much, and that's why we are getting the uh, problem with the ultrasonic detection. So now we are going to discuss about the sensing speed divide, quasi-static versus true dynamic. What are the relations are there in this two? Just a second. So speed trains directly against the multiplexing capability. Spectrum analysis scans the whole network slowly, filters integration, watches one node instantly. So in quasi states, what is the thing we need? Parameters are there: speed, which is 1 to 10 kilohertz, capacity, dozens of sensors are there, and use thermal mapping, baseline load monitoring. Those things can be done easily with quasi static sensing in healthcare. Then the second one is true dynamic sensing, filter integration. So the speed can be above 1 megahertz, but capacity limited and single sensor per filter is there. And the use case: acoustic emission monitoring, impact detection, those things comes under this. So these are the difference between the quasi-static sensing and the true dynamic sensing, where the quasi-static sensing deals with the spectrum analysis, and here true dynamic sensing deals with filter integration. Moving towards the next thing, which is tunable filter integration sweeps a fabricated cavity. So how we are going to use these things? For that, the structural graphical illustration has been given here. The broadband source, which is circulating the light and going towards the FBG gratings, and then the reflected beams will be diverted towards this, where this tunable filter, after tunable filter, it goes to the power meter. So the physics behind this is the constructive interference occurs when the round trip phase is an integral multiple of 2 pi. What about the finesse? Finesse is pi under root r divided by 1 minus r, where r is equal to 99.7%. Finesse is 1000, yielding an 12 picometer resolution within 13.7 terahertz free spectral range. You can see here that the full width half maximum is 11 picometer resolution, and the speed limit, you can see actuation relies on the physical expansion of a PGT, so which hits mechanical resonance limits around. You can see here that the piezoelectric transducer is attached with the one part of the cavity, and another part is having the reflectivity R, and because of this PGT movement, the speed limit depends on the expansion of PGT. So this is the tunable filter integration sweeps of a fabricated cavity. Now we are going to discuss about the edge filters translate wavelength shifts into intensity changes. So you know already we have discussed this one, dielectric stack. lambda by 4 thickness, which is having lambda by 4 thickness and has the alternative refractive index high low high. The mechanism is an ultrasonic pressure waves ultrasonic pressure wave stretch the FBG, its back reflected wavelength oscillates, the filters slopes slope the filters slope transmission intensity converts this into measurable power variation at the photodetector. So this is the dielectric stack where the slope transmission of the filter instantly converts to measurable power variation and at the photodetector. Whereas another thing which is translation mechanism, where the transmitted intensity and the wavelength has a measured power output threshold towards this and this, where FBG wavelength signal is mentioned here. Then the drawback is highly unscalable because the filter must precisely interact the specific FBG's wavelength. Every added sensor requires a custom engineered dielectric stack. Moving towards the next thing, what we have discussed till now, this ultrasonic detection and the earliest precursor of the structural failure, then sensing speed divide quasi-static and true dynamic, then tunable filter integration sweep, a fabricated cavity, and then edge filter translate wavelength shifts into intensity changes. Next thing is matched filters interrogate sensors using identical gratings. Core question: why manufacture complex dielectric stack when the ideal filter is another FBG? Architecture: by matching the interrogator FBG to the sensor FBG, the system naturally forms an edge filter. So this is the broadband source, this is the coupler, and then another coupler. This is the sensor FBG and this is the integrator FBG. So matching the integrator to the sensor, the system naturally forms an edge filter, and this edge filter can be used for this coupler. Using these two couplers we can make a edge filter, and this is the optical receiver system for that. So why reflection over transmission? Why do we prefer reflection over transmission? So in a transmission there will be a crosstalk from all other gratings, but in reflection strictly isolates the lambda BR band, eliminating background noises. That's why we will take the reflection over transmission beam. Now moving towards the next thing, that detection relies on the linear slope of Gaussian overlap. So if you have two Gaussian bands and want to detect two bands separately, or want to resolve it, so this is the midpoint need to use to distinguish it. So the power detected PD proportional to the integral of the overlapping Gaussian GS and GR. So this is the proportional integration of the overlapping. This is the overlapping area, and the operating point, the system is biased, so the sensor grating rests on the linear edge of the integrator grating. This constrains measurement to 100 microstrain but unlocks megahertz dynamic sensing. You can see here the dynamic oscillation, how much in this area you can see. So this is the minimum detection limit you can see based on the wavelength if you are going. Moving towards the next thing, which is minimum detectable limit require wavelength offset. So mathematical inside, the minimum detectable limit is inversely proportional to the slope of the overlap. This is the overlap. It's inversely proportional to the slope of the overlap. And then the irony of the matched filter is, if the wavelength match perfectly, lambda bs and lambda br, you can see here, this is r, bs and br, the slope is 0. There is no slope. Okay, if both are matching together like this, slope is 0. The mathematical function goes to infinite and the sensitivity is entirely lost. So if overlaps, both are overlapping each other, then the sensitivity will lost. And talking about the resolution, the capable of nanostrain resolution per under root of hertz, so under root of frequency. So optimal detection zone is 3 into 10 to the power minus 3 picometer per frequency per hertz. Okay, so this, it is coming somewhere here. Moving towards the next thing, which is the spatial gap, the blind spot of quasi distribution sensing. Now we are going towards the next thing, which is the we are taking an example of a bridge. So the blind spot of quasi distributed sensing we need to discuss here, how it happens and why, what is the limitation. So FBG are exceptional discrete sensors, but they leave vast unmonitored gaps. A failure event occurring between sensors may remain undetectable until it propagates closer. So you can't, until it is not coming to this point where its sensor is held, you can't detect it whether it's having crack or not. So you can see here, until it requires some time to propagate to near to the closer of the sensor, closer to the sensor, and then it will detect. This is the limitation, and the requirement is to achieve gapless monitoring. The core of the optical fiber itself must become the continuous sensor. So instead of keeping these FBGs here and there or at particular distances, if you can make the sensor, the optical fiber itself a sensor, full sensor, so even on a trace amount of crack or any disturbance in the structural change, structure of the bridge can be spotted easily. Moving towards the next thing, which is stimulated Brillouin scattering creates a transient moving grating. You can see that electrostrictions as a incident wave strengthens, it compresses the local silica density, forming a periodic indexing change, a transient grating. You can see here that how it is making a electrostrictions, and because of that high electric field compresses glass density, and because of this this temporal transient gratings are created, and the stock process also mentioned here, this moving grating act as a mirror, backscattering light stoke wave while feeding energy to the acoustic phonons. So high power pump waves are propagating this side, and because of the Doppler shifted stoke wave, it creates a electrorestriction, acoustic phonons, where there will be a gap. You can see here these are the acoustic phonons, and because of that the transient grating has this kind of external um, electrorestriction based transient gating, which will affect the sensing ability. So best thing is the static gating can resolve, FBG can resolve this kind of issues which are created by the transient moving grating. Moving towards the next thing, which is Brillouin frequency shift, VB, map density changes. Just give me a minute, and after that I'll come back. Okay, so we were discussing about the Brillouin frequency shift, VB, new B map density changes. The math is saying that new B, which we have discussed already, to n effective VA by lambda p. The shift depends strictly to the local acoustic velocity VA, which is 6 into 6 kilometer per second in silica, and the strain or thermal changes alter local glass density, instantly changing VA. Shifts by 50 kilohertz per microstrain and 1 megahertz per degree centigrade, which can be seen here. VB approximately 10.8 to 12 gigahertz frequency downshift, and this is the pump frequency 200 terahertz. The reflected wave Doppler shifted is coming with this frequency, downshift frequency, when the incident beam is this one. Moving towards the next thing, which is interrogating SBS, BOTDR versus BOTDA architectures. So the line width imperative, a narrow line width source is mandatory. Polychromatic sources dilutes the standing wave pattern and preventing the threshold for stimulated scattering from the being reached. And the next thing is the trade-off thing. which is BOTDR, requires access access to only one end of the fiber, and BOTDA requires a complete loop but unlocks unprecedented signal to noise ratio over extreme distances. You can see here the transmitter. This is the transmitter moving towards this thing, and has the reflectometer here itself. Shorter distance, simpler setup, and signal ended input, single ended input. So from this side only the signal is going, and the scattered thing is measured in the reflectometer. While BOTDA, what is happening in this analysis, the pump pulse will go with this direction and goes towards this, has some kind of reflected beams, and this side also, because of the transmission, the continuous probe wave, and because of that there will be a standing wave which has double-ended loop requires, and has the long haul of above 100 kilometers. Okay, next thing, which is architecture decision matrix synthesis insight, we are going to discuss. So FBG system excels at precise high speed discrete point measurement, while SBS transforms the fundamental materials of the fiber into a continuous diagnostic nerve. So you can see here the dimension, sensing mode, max speed, multiplexing, cost complexity, and best use case has been mentioned for different kind of filters. The first one is tunable filter for FE. The tunable filter has the sensing mode discrete, maximum speed 10 kilohertz, dozens per fiber, multiplexing can be done, moderate, bridge thermal baselines. Going towards the edge filter thing, it's also discrete, above 1 megahertz, one per filter, high customization, single node acoustic. Next thing, match filter. Matched filter has the discrete sensing mode, speed also above 1 megahertz, multiplexing is low or medium compared to the tunable filter. Then cost is moderate, and best use case is high multi node acoustic. Moving towards the next, which is SBS BOTDA or R, continuous discrete distance dependent. So it can be few kilohertz to few megahertz. Multiplexing finite length to fiber, it's quite high. Then extremely high cost. Also the best use cases, gapless pipeline monitoring. There is no external sensors are required like a tunable filter and FPG or FBG filters. From discrete point to the continuous nerves, as we have discussed already, the quasi-distributed lacks to understand the cracks in this region, while it can be detected easily here, but the crack, if it is increasing, then it can be detected later on. To resolve this issue, the 2D distributed sensor, which is SBS, can be used, where the fiber optics itself is a it behaves like a sensors sensor. So the evolution is optical structural health monitoring and has evolved from reading localized thermal shifts to listening to high frequency acoustic precursors. Then the horizon is stimulated Boolean scattering removes the final physical limitation, the spatial gap, the entire structure is no longer just monitored. It is fundamentally sen- sensitized. So, from the discrete point to continuous uh, detection is the key which we have discussed till now. In this wave length tunable sensors, and today this is the last session for the wavelength based sensors. Next week we are going to discuss about another sensor, another detection sensor, and till now we have already covered all the wavelength dependent wavelength modulated sensors um, discussion. Now we'll take 5 minutes break, and after that we'll go to the question answer session. Before that, if you have any doubts, you can ask me. Just give me 5 minute break. Okay, so you, Janani, you have any doubts? You can ask me.
No, sir.
Okay, so we'll move towards the question answer session then. You have to give answers. I'll I'll cross check and after that we'll discuss. Okay. Hmm. How did you see your marks in weekly those assignments? Did you get those ones?
Yes.
How you are doing actually? I don't know any. I'm not
Average,
aware.
sir, like
7, huh?
7
From out of.
out of 10. It is for 100, so 70, 60, 80. It's changing for every.
Okay, okay. So you planning to give the main exam, final exam?
Yes, sir.
Ah, then it will be good. You you'll qualify quite nicely. In a in a yeah, you do better in the final exam. Okay.
Okay, sir.
Hmm. Okay. So we'll go one by one question. This time the questions are quite a little bit hard. So, but not that much. You can answer it because you are doing the assignments and assignment questions are quite harder than this compared to my questions, which I am going to display here. So the first question is, in a diffraction and CCD based interrogator, how is it possible to achieve a resolution of better than zero point 0.5 picometer despite having a pixel spacing of approximately 0.15 nanometer? Option A, by using a narrower diffraction grating line. Option B, by reducing the scanning speed of the CCD element. Option C, by increasing the number of CCD elements to 1024. And option D, by fitting the collected data points and interpolating between them. Are you able to see questions?
Yes,
Okay. Are any blurriness is there?
it is clear, sir.
Maybe I'll increase the size of the question. Just give answer according to you. You can type or you can discuss also. You can give answer option A, B, C, D. This one we have discussed in the last class, last session. How we are able to detect over the limits, beyond the limit.
Option D.
Option D, huh? Okay. Yeah, so option D you are saying by fitting the collected data points and interpolating between them. Yes, it's correct. So last time also we have discussed about this, that how we are doing this in a CCD based interrogator. Okay, so you are correct. Moving towards the next question, for a Fabry-Perot interferometer, what is the mathematical expression for the finesse f of the cavity in terms of mirror reflectivity r? Tell me what is the
Option B.
B. Okay,
B.
this one.
Yes, sir.
uh, just now we have discussed about this finesse pi by pi into root r by 1 minus r. Yeah, this is also correct. Moving towards the next question, when designing a tunable filter of bridge monitoring with a spectral width of 110 nanometer, why must the free spectral range FSR B. At least 110 nanometer. Option A. To allow the piezoelectric PZT element to vibrate at higher frequencies. B. To ensure that only one transmission peak is present within the measurement band. C. To maximize the reflectivity of the fiber based mirrors. D. To match the bandwidth of the broadband source exactly. What could be answer here? Give your answer.
Option C.
To maximize the reflectivity of the fiber based mirror. Reflectivity doesn't depend on the spectral width, no. Reflectivity is the independent thing. So this tunable filter of a bridge monitoring with a spectral width of 110 nanometer. So this why must the range should be at least 10. So to allow with higher frequency it is not required. To maximize the reflectivity this is also not correct. To ensure that only one transmission peak is present within the measurement band. Yeah, this is correct actually. So what is happening in this FSR should be lesser than the what is it, spectral width. Okay, so it should be just a second. Yeah, so not this one, spectral width. Let me check once. So yeah, so FSR should be greater than the spectral width, which is 110 nanometer. If you have less than 110 nanometer FSR, then what is happening is it will makes noisy what we say it will create so much acoustic noise, and because of that we will not get the proper tunable filter for breeze monitoring. So that's why we need to have the FSR range should be at least minimum 110 nanometer, equal to the spectral width, or greater than 110 nanometer is always okay. And to match the bandwidth of the broadband source exactly. No, it is not required. It should not. It is not required to have a match every time to the broadband. Okay. Moving towards the next question, which is in the context of structural health monitoring, which measurement strategy is considered the most cost effective? Optimum by utilizing continuous monitoring. Option A, breakdown maintenance. Option B, corrective maintenance. Option C, condition monitoring. And option D, preventive maintenance. Let me know your answer.
Preventive maintenance.
Preventive maintenance. Repeat. No, this is preventive maintenance is not correct answer.
Condition monitoring.
Yeah, condition monitoring is the correct answer. Where that vibration and the acoustic both measurements. What is this? Acoustic maintenance monitoring like vibration and acoustic, and the measurement is balancing between the measurement and operation. So I already discussed about this one, this plot, where the minimum cost is relying. So this is based on the condition monitoring. Going towards the next question, why are spectrum analysis techniques such as tunable filters generally unsuitable for true dynamic sensing of ultrasonic waves 10 kHz to 1 MHz? Let me know. Ultrasonic waves do not cause a shift in the Bragg wavelength. The medical or sequential scanning speed is limited to the kilohertz range. Option C. The optical power of the FBC reflection is too low for detection, and the option D. Diffraction grating cannot physically resolve ultrasonic frequencies. What could be the answer here?
B and D.
Yeah. So here the option B is the correct. The mechanical and sequential scanning speed is limited to the kilohertz range. And why is it so? Because in the tunable filter, the spectrum analysis is used by either CCD or PZT. So this piezoelectric and CCD charge coupled device has the needs to operate at the few kilohertz frequency or in a kilohertz frequency. It can't achieve the megahertz frequency because of the mechanical movement. It will not able to tune that much fast to achieve or to capture the megahertz perturbations. So that's why this mechanical and sequential scanning speed is limited to the kilohertz range. Okay. And the second thing you are saying the D, why is it not so? Because diffraction gratings cannot physically resolve ultrasonic frequency. No, diffraction grating deals with the wavelength, not with the frequency. So perturbation is a temporal use. Okay, so the frequency of the perturbation is temporal condition, not a spatial resolution. Okay, so lambda is diffraction grating is for the lambda wavelength. Next question. An edge filter constructed from a dielectric stack uses alternative layer of a high NH and low NL refractive indices. What is the required thickness of each layer D to maximize constructive interference at wavelength lambda? Let me know your answer. Constructive and destructive interference. So constructive, how we can achieve?
lambda by 4 in option C.
Option C.
C, yes.
Why not option D?
The condition is pi by 2.
Okay, so it's because of the quarter wave thickness. Okay, so it's like the what is the required thickness layer D to maximize constructive interference at lambda. So yeah, so the lambda by 4 thickness ensures that the uh, for the maximum constructive interference can happen. Okay, yeah, so you're correct. Question number next question. um, in a match filter integrator using two fiber Bragg gratings, why is the reflected configuration preferred over the transmitted configuration for multi-sensor integration? Option A, to eliminate background light and reflections from unrelated gratings. B, reflected configuration do not require the use of optical couplers. C, it allows for the use of cheaper LED sources. D, the reflected signal power is naturally higher than the transmitted signal power. Let me know your answer.
Option A, sir.
Okay, so option A, it eliminates background light and reflection from the unrelated grating. Yeah, it's correct. You are correct. Moving towards the next question. The sensitivity of a matched filter interrogator is determined by the slope of the overlap between the sensor FBG and the filter FBG. At what relative wavelength position is the minimum detectable limit best sensitivity achieved? Option A, when the Bragg wavelengths are identical, lambda Bs is equal to lambda Br. B, at the linear midpoint of the transmission slash reflection flow. C, when using a broadband source with a spectral width of less than 1 nanometer. D, when the sensor wavelength is completely outside of the filter. What is your answer? Give your answer.
Option A, when it is 0, sir. Option B,
Option B.
option A is 0.
Yeah, yeah. So when the identical, it is the um, um, what is it? Peak of overlap will be, the slope is 0. At the peak of overlap, slope will be 0. But at the midpoint of the transmission and reflection slope, it will be maximum. Here. So this is the correct answer for that. At what relative wavelength position is the minimum detected limit best sensitive achieved? So obviously at the maximum slope we can achieve best sensitivity. Moving towards the next question, stimulated Brillouin scattering (SBS) is a non-linear process resulting from the interaction of light with which type of particles or wave within the fiber? Acoustic phonon, free electrons, atmospheric pressure wave, optical phonons.
Option B, acoustic.
Yeah. So SBS is a nonlinear process resulting from the interaction of light with acoustic phonon of particles or wave within the fiber. Okay. So your answer is correct. Moving towards the next question. What physical effect causes the periodic changes in the refractive index that creates a transient grating during stimulated Brillouin scattering? Option A, thermal expansion; B, the Doppler effect; C, electrostatic; D, photobleaching. Give your answer.
Doppler effect, option B.
Mm, partially correct, but we have already discussed about this one. The physical effect cause the periodic change of the refractive index is because of the electrostations. We have already discussed about this. Doppler effect is mostly focused on the frequency shift. Okay, so because of the frequency shift, but um, it will not explain why and how the mechanism of to create the index modulation itself. Okay, so this is not correct. Electrostations, I already discussed about this. High electric field creates the movement standing wave pattern to change the material density. Here you can see electrostation, and because of that this transient grating is occurs instead of the static grating. Okay, so the correct answer is electrostation. Next question, in a standard single mode silica fiber with the effective refractive index of 1.46 and the acoustic velocity nu a of 6 km per second, what is the approximate Brillouin frequency shift nu b for a pump wavelength of 1550 nanometer? Let me know your answer. This is a numerical kind of thing, but just you need to calculate the nu b, which is equal to, you know already what is the equation. Calculate and let me know what is the answer. Anything? I think you know the equation. At least if you tell me the equation. Nu b is equal to
Two A mu A by lambda.
2n effective nu a by lambda, and we know that lambda is given here, nu a 6 km per second, n effective is given here. If we keep all these things, we'll get 2 into 1.46
Option A.
120 megahertz, 6 kilometer per second, then divide 1550 nanometer, so into 10 to the power, in meter it will be 8, but kilometer it will be how much? 11 kilometers. You calculate this, how much it is coming, see, or you can calculate this one now. This one, instead of kilometer we can write 6000, and this can be written as 10 to the power 8 9. What is happening? 9. Oh, 9, yeah, 9 meter. Here also meter. Let's calculate. I'll also try to calculate. Into 1.46 into 6000 divided by 1550. Anything I'm missing or what? What is right? Minus 9 here. So it's coming almost
11 gigahertz. Option C.
option C, yeah. So it's coming approximately in gigahertz. So let me check one more time. 1.46 into 6000 and to the power 9 divided by 10. Yeah, so it's coming 3. Yeah, it's coming in gigahertz. 10 to 10 to the power some gigahertz. It is coming 11 point something gigahertz, but the closest answer is this one, 10.8 gigahertz. So this is the correct answer for that. Okay. Next question is, I think this is the second last question. What is the preliminary advantage of stimulated Brillouin scattering (SBS) sensors over fiber brag grading sensors in structural health monitoring. SBS can be used with broad spectrum LED sources. Option B, SBS is insensitive to temperature, eliminating the need of discrimination techniques. Option C, SBS enables truly distributed sensing along the entire length of the fiber. Option D, SBS sensors are significantly cheaper to implement than FBG systems. Let me know your answer. This is just
Option
an
C, sir.
Yeah, you are correct. So we already have discussed about this one. This is not correct. It's very costly technique. Insensitive to temperature. No, it is sensitive to temperature. It can be used for broad spectrum LED source. No, it needs pulse laser. Only the correct thing is truly distributed sensing and very high cost. Okay. Our last question is, which of the following is this last? Yeah. Which of the following describes the key limitation of using stimulated blue line scattering for high speed dynamic sensing? Option A, the requirement of cryogenic cooling of the sensing fiber. Option B, the inability of acoustic phonons to respond to strain changes. Option C, the time required for the light pulse to travel the length of the fiber and back. And the last option, the total lack of sensitivity to compressive strain. Let me know your answer. Guess anything if you can.
Option C.
The time required for the light pulses to travel the length of the fiber and back. Yeah, correct. So what is happening here is like it is depending on the only on the time of flight. It's a OTDR system, and everything depends on the time of flight. And the maximum sampling rate is the only limited by round trip time of light in the fiber, and that's how this is the correct answer. It doesn't require any cryogenic cooling. Inability of acoustic phonon to respond to strain changes, it's not required because we are not having any kind of gratings here. Whole fiber itself is working as a sensor. Total lack of sensitivity to comprehensive strain, this is also not correct. Okay, so we have already almost completed the live session, and now if you have any doubts you can ask me. Otherwise we'll meet tomorrow afternoon to 2 o'clock. Extra session is there, extra live session, so we'll be having the discussion tomorrow. It will be just a question answer session. Also I'll just cover whole things whatever we have discussed from week 1 to week 11. Everything we will discuss in the one session. I don't think so we will be able to discuss that much, but we have 2 hours, so step by step, one by one, we'll discuss different kind of modulations and what are the limitations with that, what are the advantages with the various modulations sensors. Okay, up to the wavelength one. After that we'll see one more is there. We have completed phase, amplitude and wavelength. The last one I forgot the name, let me check.
Polarization.
Yeah, polarization, yes. Polarization based modulation is also there. That will be covered in the next live session, which I will be um, taking the live session on 9th, Thursday maybe. Yeah, because 11th I'm leaving to France for a conference, so I won't be able to take the live session on Saturday. So that's why I'm preponing it to Thursday.
Thursday evening 6 o'clock.
Thursday the same time, I think 6 to 9.
Okay.
Yeah, Thursday and tomorrow also there. One live session full recap we will be having tomorrow 2 o'clock to 4 o'clock.
Okay.
Yeah,
Thanks.
yeah. So we can also discuss more. If you have any doubts, you can ask from the starting onwards. Week 1 to
Yes.
week 11. Okay. Okay, then we'll meet in the next live session then. Did you contact Professor?